Hi, my name is Eldrich Rebello, and I'm with the Wind Energy Institute of Canada in Prince Edward Island. This is our presentation titled Evaluating the Performance of a Wind Generator in Providing Droop Control During Grid Frequency Increases. That's quite a long title, so let's break it down. What was tested? Droop frequency response of a single wind turbine. This response is similar to Droop's speed control of a synchronous machine in that active power works to counter a grid frequency change. Where was this done? At the Nutby Mountain Wind Farm in Nova Scotia, in Canada. Who was involved? Nova Scotia Power, Enercon Canada, and us, the Wind Energy Institute. Funding came from Natural Resources Canada. I'd like to briefly emphasize 2 points. One, the value, and two, the last few words of the title, the independent analysis bit. The value here is that what we present is empirical data. This is not a simulation. This is an independent analysis because the analysis was done by us and we have no conflict of interest in reporting everything that we found. Briefly, the participants involved here, there were three. Nova Scotia Power, their role was as the utility and the farm owner. Enercon Canada were the wind turbine OEM. And of course, us, WEICan, we were responsible for project administration, analysis, and reporting. I just want to take a moment to thank everyone involved in the project for working through the delays caused by the COVID-19 pandemic. There was a significant delay and a lot of work involved, so thank you. The background and summary of this project. You can see here a map of the province of Nova Scotia. You can see the location of the wind farm marked. And this is one of those maps where up is not north. So this has been rotated slightly. And the Atlantic Ocean is off to the bottom and the right here. The wind farm has 22 Type 4 wind turbines. It's been operational since 2010 and it's connected to the provincial transmission network. The context. Nova Scotia is a province in eastern Canada on the Atlantic coast. The province's share of renewable energy has been increasing, and as of 2019 it's around 18% of annual electrical energy. The off-peak load on Nova Scotia's grid is around 700 megawatts in the summer months, and the installed wind capacity is around 600 megawatts. You can see that the two numbers are fairly close, and this creates reliability challenges during periods of light load. The solution at the moment is to use thermal generators, which are kept online. However, the province phrased the question here as such. How can wind generators provide some of the ancillary services that currently come from thermal generation? So to that end, we tested three ancillary services on the wind farm. There was fast frequency response, sometimes sold as synthetic inertia. There's power frequency response, which is what's presented here, and AGC, or automatic generation control. The future work will cover number 1 and 3 on this slide. However, let's talk about the droop frequency response here. I'm aware I've been using two terms here. This is because droop frequency response is sometimes sold by Enercon as power frequency response. What this is quite simple. It's very similar to droop speed control in a synchronous machine. So if grid frequency were to fall, you would expect generator active power to rise. Conversely, if grid frequency were to rise, you would expect generator frequency to fall. However, you can see from this plot here that there's a bit of text saying reserve power. As you expect, you cannot increase a wind farm's output above what is available in the wind. So to provide the power increase here, you would need constant power curtailment. Now we did not test that. Instead, we only tested the response to a grid frequency increase. How this was done is fairly simple. We injected a 100-second long over-frequency signal into the wind turbine's control system. It detected a frequency rise, and it would then initiate a power curtailment response. We would gather data and repeat this at several power levels. Here's one example of the kind of data we gathered. You can see the injected frequency here in red, And you can see that at 60.5 Hertz, which is the trigger frequency, the power curtailment response is triggered. So there's a reduction in active power output, and that reduction follows the expected response here, which we show with green crosses. This response was calculated based on the frequency deviation. So how far is grid frequency changed from nominal and the initial power level. So you can see here that across the 39 runs that we tested, we have a good spread of wind speed and power data, right from cut-in all the way up to rated. To emphasize two things here, we tested this on a single turbine, so not the farm as a whole, just one turbine, and we tested only the response to frequency increases. Now, this is what our full set of results looks like. Now, I don't expect you to be able to read any of this. It's just there to show you that we do have quite a lot of data. One analysis that we ran on the data was the average error. So this is the difference between the expected response and what was actually measured. You can see the magnitude of each run here. You'll see from the upper half of this plot that the error was quite low. Across all the data we have, the mean error is around 50 kilowatts or around 2% of rated power. Now to put that in context, this is 50 kilowatts on a wind turbine that's rated at 2.3 megawatts. The outliers here at the bottom, these are due to falling wind speeds. So what's happened here was that the response duration, so the frequency signal we injected was 100 seconds long, and during some of the runs, wind speeds were decreasing during those 100 seconds. So because the expected response is calculated using the initial power, sometimes the expected response was not met. So that's the reason for the error here. Some of the challenges we ran into, this is field work. So as with any work in the field, there's a challenge in coordinating and planning this. However, here we were lucky in that the system operator and the farm owner were the same person. Gathering data requires specialized equipment. Unfortunately, the equipment we used required an operator on site. So you can imagine that this was a challenge, especially considering the COVID-19 travel and quarantine restrictions. Finally, why would you go through all this effort to gather this data? Well, simulations are much simpler and easier to run. However, they provide more broad strokes data, and there are lots of assumptions that go into simulation models. What the data we've presented here is from commercial wind turbine technology and is easy to replicate. So you could expect that if you had a similar wind turbine with a similar drivetrain, you would expect a similar result. So in conclusion, what we tested here was group frequency response to grid frequency increases. The response was as expected in that power was curtailed proportional to the frequency deviation. So this is one more ancillary service that could possibly be offered by wind generators. So the one sentence summary of this work could be put like this. You can reasonably expect a wind farm to curtail its active power output in response to grid frequency increases, and this can contribute to grid stability by allowing time for other control measures to activate. Now, of course, the data we have here will soon be published along with further analysis. Finally, I'd like to thank the three project partners here, Natural Resources Canada for their funding, and Enercon and Nova Scotia Power for their time and equipment and their cooperation through this entire work. Thank you.